We are doing the Gauss law problems, and we did few questions due to point charge, and we saw the variety of symmetricity, right? Like spherical, cylindrical, and planar. So have you done those part, the symmetricity part?
Yes, sir.
Okay. So have you derived the formula for the line charge? No, I don't.
No, sir.
So today we'll derive the formula. So are we done with the sphere part?
Yes, sir. We have completed this figure part, sir.
Yeah, I gave you one homework like rho equals to rho not 1 minus r.
Yes, sir. I'm getting the maximum at 2 by 3 hours, sir.
Yeah, that's great. That's good. That's the right answer. Excellent.
Yes, sir.
So let's do something one like this. So this is A, sorry, this is B, and this is the volume density is rho, or let's call it Q. Okay. And we have one more charge at the center. So the question is find E in all the three regions 1, 2, and 3 as a function of R. So R is the in general distance from the center to the point. So tell me what is the answer? What are the answers actually? So I kept the lecture today so early because in the evening I have to catch a train and tomorrow I will be in the Mumbai. So that's why I kept lecture today at this time.
Sir, in the evening, I'm also having chemistry first lectures.
Ah, great.
So
Yeah,
for the first region, I'm getting it as like k small q by r square. So,
excellent. That's correct.
sir, for the second one, I'm yes, sir.
R 0 to A, right?
Yes, sir.
Next,
Sir, for the second region, I'm getting it as k into q plus q into r cube minus a cube by b cube minus a cube
excellent. Very good.
divided by r square.
Very good.
Sir, and for the third one, yes, sir.
Excellent. Okay, so this is the answer for all the three cases. Now, what they can do is only variation. So maximum you will get a variable rho formula, and then you just do the integration to find the charge enclosed, and from there onwards we'll get the answer. So, now we'll go for the next part, which is called E due to uh, due to spherical cavity. Now this is very very important. Not due to, it's a just inside spherical cavity. So let's say you have a spherical charge and you make a cavity within the spherical charge of shape which is also spherical. So the cavity itself is spherical. The
Yes.
center, let's say the radius is capital R, or okay, I'll just make it a different. Let's call it A, and the radius of the cavity, let's call it B, and the separation between them, let's call it C. And the volume charge density is rho, and I'm assuming, I'm assuming it's a uniform. So the question is, what is the value of electric field at any point within the cavity? So at this point, let's say a random point.
Sir, it's 0.
Uh, okay, so but how you call it zero? Because charge enclosed is zero. That's why.
Yes, sir.
But if you look carefully, is it symmetrically arranged with respect to the outer sphere? Is it symmetrical point?
No, sir.
So when things are not symmetrical, then the guess will not work. So we cannot guess it actually. Because charge enclosed is not the criteria for the electric field to be zero. I'll prove it later on why it is so. What matter is the distribution of other charge. Okay. What matter is the you can say the geometry, the symmetry, and everything else. So what we can do again here is you can use the negative charge concept, and because vector electric field is a vector quantity, so we have to find the electric field at point P due to full sphere, due to the cavity sphere with a negative charge, or you can simply assume the positive charge, or okay, like this. So what I'll do is, this question is equivalent of taking a full sphere and try to find the electric field at the point P and then you subtract the answer that a sphere of this size would have created at the same point P. So the point P is same for both, but it will locate like this, right? So the O dash will tell you P is here, and O will tell you P is here. So whatever is the contribution, whatever is the contribution of the net field at the point P, so this will create a field like this.
Yes, sir.
So get a field like this.
Yes, sir.
If I call the field as E1 vector, if I call the field as E2 vector, then the net field at the point P, because it's a vector quantity, so we have to use the principle of superposition within vector form. We cannot write in scalar form because the point is such that the E1, E2 are not in the same direction, right? They are not
Yes.
parallel. So we write E1, but we must take the difference or subtract the contribution that this sphere would have created, assuming the same charge. I'm assuming it's the same charge. Okay.
Okay, sir.
So that is how you can imagine, or you can say the other way of doing this, you make a plus here, but make a minus here. Then you have to reverse the direction. Then you will add the value. Okay. So that's why we keep everything positive the way it is, and we subtract the value because we are trying to remove the contribution that the small sphere would have created being alone. Okay.
Okay, sir.
So now how we are going to write it? So these are like full sphere, complete sphere individually, and the point P is within the sphere, and we know the formula for the electric field due to uniform sphere, right?
Yes, sir.
And the formula for the uniform sphere is rho r by 3 epsilon naught. So this is the very important formula which we must remember. So rho r by 3 epsilon naught, and therefore you can write this as rho. Now what is r for the first big sphere? OP vector.
Yes, sir.
Because in vector form we write r vector like this upon 3 epsilon naught minus rho O dash P vector upon 3 epsilon naught. Eventually what we will get here is rho upon 3 epsilon naught and what is OP minus O dash P? OP minus O dash P is how much? So you have to come back to the triangle, this triangle
Yes.
here. I mean, I have to create a triangle here. So this is O dash P. This is OP. And this is O dash. So in a triangle, from triangle
So O dash.
O dash vector plus O dash P vector is OP vector. So O dash is equals to OP minus O dash P. And therefore this turns out to be rho upon 3 epsilon naught into O dash. Now this is a very, very significant result. It will have the repercussion in variety of problems. And what it says that no matter which point you choose, the answer will not depend on the point P. Because you can see I have taken a point P, but the P is not in the final answer, right? So
Yes,
rather
sir.
P depends on the sorry, electric field depends on the separation between the center. Separation
Between the center.
Now if I create a concentric cavity, then the O dash becomes 0.
Yes, sir.
Then the field will be 0. Understood?
Yes, sir.
So now you realize that why only concentric cavity can create the 0 field. The cavity which is not concentric cannot create 0 field. Okay.
Yes, sir.
From India plus 918828349727.
Okay. So the whole idea is cavity may not have charge. It doesn't mean they will not have the field. They will have the field. Only when they are concentric, the field becomes 0. The moment they are not concentric, there will be electric field. And that is logical, no? Because see, I can assume that everything will cancel out, but the mirror image of this cavity, the charge here, this will have the net effect here, isn't it? So
Yes,
this
sir.
will charge create some effect. So other may cancel out, but something will be there. So calling this as zero is not a good idea. Yeah. So
Yes,
now
sir.
in magnitude, okay. So the modulus of electric field in the cavity, we can write as rho c by 3 epsilon, right?
Yes, sir.
The numerical value is OC because the length of O dash is C only, right?
Yes, sir.
The separation between, if you remember, I have told. So the separation between O dash is C. So this is a C value, and therefore, and what about the direction?
Sir, O dash.
Parallel to O dash.
Yes, sir.
So direction of field inside cavity will be parallel to O dash. Understood?
Yes, sir.
And therefore, now, oh, sorry, this is not required. Therefore, if I want to represent the field so once we know the center of the black and the this one, so once we know this is O dash, the electric field in the cavity will be parallel to this line and everywhere. So it is like you create a uniform field within a spherical cavity. So this is a really nice way to create uniform field, isn't it?
Yes, sir.
And now because the field is uniform in a way, constant in value and direction both, you can actually treat this as a like a, if I take a small piece of it and if I zoom it, so it will look like a uniform field like this.
Yes, sir.
So we can also solve the question of motion of charge particle in this uniform field. And the only difference is the value of E will be rho mod of O dash vector upon 3 epsilon naught. So if we have a, let's say, charge particle inside the cavity, then it will actually move under the influence of this field. Understood?
Yes, sir.
So the force on this charge particle will be how much? The
So
force will be
QE.
Q. Then you can find the acceleration as QE by M.
Yes, sir.
And then you can add the kinematic equation, S equals to ut plus half t square, v equals to u plus at, and so on, right? So
Yes.
those kind of question you will come across in this particular concept. So of course the step is to find the field first, okay, and then get the calculation done. All right.
Yes, sir.
Okay. So next we can do is a similar problem, but in a different way it is put together. So we have two sphere, one with positive charge density, and another is also there with negative charge density. This is negative, and the center, if I join the center of the two, let's call it D. So now if I ask you what will be the electric field in the common region somewhere here at point P, can you guess the answer?
Yes, sir.
So again apply the same
Like,
superposition.
okay, sir.
So first you try and then I'll tell you what to do. So they see here there is no cavity, but actually the plus minus will cancel out. So there is a cavity like shape. So the common region is having no charge, right?
Yes, sir.
So that is how you have to think about. So you have to use the principle of superposition again to come to the answer. So try this out and tell me the answer.
Okay, sir. So,
Yeah.
sir, rho by 3 epsilon naught into O dash vector.
Yeah, exactly. So it's again the same answer, right?
Yes, sir.
So this question, these kind of questions are very common, and so the G advanced problem.
Okay,
So
sir.
the field will be here. So
Yes.
the field will be parallel to the O dash, right? Something like this.
Yes, sir.
All right. So whenever we have a cavity, so now let's take this to the different level. So if I take this to a level in which so we have a, let's say, a hollow shell, and we have some positive charge here, which is non-uniform, and then we have the negative charge, which is also.
So I think the positive charge distribution itself is non-uniform.
Yeah, and the negative charge is also non-uniform. So this question is, at first go, it will look like something very weird, but eventually you will realize that this is equivalent of the complete positive sphere almost overlapping with the so if I slightly move this way, it is like they are just missing the edge, right? The rest is collapsed.
Yes, sir.
So if I take the gray one as the positive and the orange as negative, you can see we have a layer which is having different values. The layer is not uniform, so we have a different thickness of layer coming here,
Yes,
right?
sir. Yes, sir.
Let me exaggerate the layer so that we can see it clearly. So what we can realize that this creates a positive layer with non-uniform thickness, and this creates a negative layer with non-uniform thickness, and the remaining is like the collapse of the two layers, right?
Yes, sir.
So what they are giving is sigma. So we can define sigma here. So you will realize something here. So it is like the center is same, but thickness is varying. If I draw a patch, if I draw a small patch here, this is like cylinder, and also what we can realize that the center, these two centers are coinciding, yes or no?
Yes, sir.
No, these centers are not coinciding. That's why they are like not completely superimposed. They are same size.
Oh, right. There'll be a little bit of distance between the two
Yeah.
spheres.
And that is, I mean, that is required to create the field. No?
Yes, sir.
If they are concentric, then what happens? We don't have any field, right?
Yes, sir.
So what we realize that it creates a positive center and a negative center. A positive center and negative center, and the gap is how to represent this. So the center is actually displaced. So we do have O dash here. I think black will be better. So we have O and we have O dash. There is a small gap. We don't, let's call it D.
Yes, sir.
Okay. So now, if this is theta, then we know the relation between sigma and rho formula. So rho depends on, because the gap is D, so the maximum separation is here. This is like D.
Yes, sir.
So actually, I mean, this is I mean, of course, this is difficult to scale, but let's just make it as small as possible. So what you can realize that the D, the thickness, sorry, the gap between the two. Let me remove this part. I hope you can realize this part. So the maximum gap you can see at the topmost point, right? So the D here and the D here will be same.
Yes, sir.
Okay. Now I would like to know, if this is a D value, what is this thickness at angle theta? So how to relate the D with the angles? Because as you go towards right at 90 degrees, the angle is 0.
Yes, sir.
At this the angle we can see the thickness is 0, right? No thickness. And
Yes,
the
sir.
maximum is, so if theta is 0, we have maximum thickness, and if the theta is 90, we have no thickness. So it looks like the thickness varies with D cos theta, right?
Yes, sir.
So this is like a D. Okay, sorry, color change. So the gap is here is D cos theta. Okay,
Yes, sir.
and we know that how to relate sigma with rho. So volume density into volume, which is dA into D cos theta. If you remember what I mean to say,
Yes,
surface
sir.
area into thickness is equals to sigma into dA. Both are same.
Yes, sir.
So dA will cancel out. So what you can realize that rho into D into cos theta is equals to sigma. So sigma is a function of theta. So if I call the rho into D, so rho into D is the sigma at this location. Let's call it rho naught. So at theta equals to 0, can we define sigma as sigma 0? Right?
Yes.
Then we have a formula that sigma at an angle theta is sigma 0 into cos theta, isn't it?
Yes, sir.
So this is the reverse creation problem. So in the examination, I mean the actual question, they had given sigma as sigma not cos theta. And what we're doing is we're creating the relation indirectly. So actually, the sigma at theta equals to 0, if I call sigma naught, automatically it becomes, because sigma naught is rho into D, no? Because thickness is D there. Correct?
Yes, sir.
Now, when we have the positive charge and negative charge at some difference, when we have positive charge and negative charge at some difference, then it becomes a dipole. So we'll come to know later on that this is like a dipole. So there are many ways to interpret this, but this is the first interpretation we are trying to understand here. So this question is, now we are converting into a new problem in which we have a positive charge and negative charge. And what you can realize that the electric field will be uniform throughout the volume except the surface, right?
Yes, sir.
So can we say that we have electric field going to be like this?
Yes, sir.
Parallel to O dash, if you remember.
Yes, sir.
It is clear.
Yes, sir.
So these all questions comes in the same category. That's why I have to present it here at the same time so that you can understand what is happening here. Okay.
Okay, sir. So is this question a PYQ of sorts?
Pardon? This question is from Erodov actually.
Oh.
And this is one of the most challenging problem from Erodov.
Yes, sir.
And now the question is how to write the electric field value. So electric field value is how much? If you remember, E.
Sir, sigma, rho D by 3 epsilon naught only, sir.
Let me cover this part. I mean, in a different box so that you can understand. This is not a question. Not to get confused with. Yeah. So that question is there. Now we are solving here. Yeah. So the answer was the electric field in the cavity we write as rho D by 3 epsilon naught, right?
Yes, sir.
But rho D itself is sigma naught.
Yes, sir.
So you can see the electric field that we'll get is sigma naught by 3 epsilon. That's interesting answer.
Yes, sir.
So you can see from where to where we can create the question. So this is actually a very challenging problem, but because we have seen the process by of creating the problem. So we are okay with the idea that okay, this is how it is being created. Okay, and
Yes,
then
sir.
later on you will also study about the dipole moment, which is nothing but the charge into its separation. So positive charge into negative charge, like positive charge or a negative charge, you take a magnitude, and when you multiply with the separation, it becomes dipole moment. So you might have studied in school that if you have a minus charge and if you have plus charge, Q and Q, and if the gap between them is, let's say, D, is then the dipole moment we write as Q into D.
Yes, sir.
Okay, Q into D, and the Q is the total positive charge, or you can take total negative charge as well. Understood?
Yes, sir.
So therefore, I mean, let me go to the next page. It's too much. So I will teach you dipole. This is the last topic of the chapter, but right now I have to use it for some reason. So the dipole moment we write as the charge, take a positive charge into D. D is called the separation between the center of positive and center of negative charge. And if you try to write the charge value, it is rho into 4 by 3 pi r cube. That's r is the radius. Okay. Into D.
Okay.
You can see that this is as good as rho into D into 4 by 3 pi r. Okay. This is like a sigma naught. So sigma naught we can also replace in terms of dipole moment, which is like a 3 by, I mean, like this. P upon 4 by 3 pi r cube, isn't it?
Yes, sir.
So the electric field will be sigma naught by 3 epsilon naught. This is what we got, right? So
Yes,
we
sir.
can write as P upon just a moment. So 1 by 3 epsilon naught multiplied by P upon, so sigma naught is P upon 4 by 3 pi r cube. You can see the electric field in the cavity is P naught upon 4 pi epsilon naught r. And later on, if you know the formula, the 4 pi epsilon naught is called K.
Yes, sir.
It's like Kp by r. So these are multiple ways in which this answer can be interpreted, and these are really nice looking values. So K is here 1 by. So later
Yes,
on we come to know like why we are writing like this, but these are the formal derivations. So actually the question here was, we have a shell in which sigma is sigma naught cos theta, and this is given, and you have to find the electric field at the center. So, or electric field in the cavity. So the answer is simple. The electric field in the cavity is sigma naught by.
3 epsilon.
So now this is a derivation. Like this is how the reverse process. Like we are trying to create a question like this. Okay.
Okay, sir.
All right. Okay. So that's okay. So we can do this. And yeah, this is done. All done. So you have to just be very careful with this question. This is one of the most just Okay. So now we can move to the next concept. So you got this answer, like how we create the problem.
Yes.
So this was a very, very, important discussion, and just keep in mind that questions like this will come in future also.
Yes.
All right, so let's go next. So next we can go to cavities done. Okay, now we can go to the line charge. So electric field due to infinitely long line charge. So again, because we have line charge and that is infinitely long, so there are two ways to interpret it. So first way is it is really long. Yeah. The other way of thinking is, so we do have a finite line, but the point is so close that it looks like infinite. In both cases, we can apply. It means the idea of infinity is always relative. It has need not to be like actual infinity.
Yes.
So
Sir.
if you are really interested in finding the electric field very close to the wire, there is no problem with the assumption that it is infinite. The same is the same is true for the disk also. So if you are really close to the disk, you can assume it as infinite. If you are close to a cylinder, you can think as infinite. If you are close to a sheet, you can think as infinite. So in both cases, the derivation will hold true. Okay. So the infinity should not be taken in the context of dimension, rather in context of the relative dimension. And relatively, we have to check for the answers. It is clear?
Yes, sir.
So if I ask you find the electric field at a point P, which is located at a distance r from the line charge. Okay. So the point P is r distance away from the line charge. So first of all, we need to know before applying the formula, of course, know that which kind of symmetricity we are going to expect. So the field lines will be following which symmetricity?
So cylindrical or like radially outward.
Yeah.
In a one.
So we must draw a cylinder which passes through the point P and concentric with the line charge, right?
Yes.
So you can draw a cylinder of any length. Length it doesn't matter, but because we have to draw what we call concentric cylinder, which is a closed Gaussian surface. Which is a closed Gaussian surface. Now the length really doesn't matter, but we can choose length as well. And we know already in advance the electric field at the point P is going to be radially outward, and not just P, in fact, every point on the curved surface. So if you choose any patch over the flat surface, the area vector will be like this.
Yes.
And because the area vector is like this, no electric field will pass through the surface, right? Because the electric field is radially outward, right? Like this. So the flux contribution from the two flat surface will be how much? 0.
Yes.
And because the flux contribution from the top and the bottom is 0, so only flux we get from the lateral surface. And therefore, although it's a closed surface, but the area that we are really interested in is the curved surface. So what we can write is E into the curved surface area. And the curved surface area is how much?
Yes, sir.
So the if I say that E is the value of electric field at every point on the curved surface, because that is symmetrically placed, so that must be have same distance r. Therefore, the E must be equal in value. So the LHS will be always this much. LHS of the Gauss law, because the Gauss law says that E dot dA over the closed surface is Q enclosed. So this will actually become E dot dA. So this is like through surface one. Let's call it S1. S2. And the curved surface. But the first two terms are 0, right?
Yes, sir.
So they won't contribute. And that's why your answer is only curved surface. That's why the LHS will turn out to be. And the RHS is the charge in the box, in the Gaussian surface. How much charge you can see inside?
Sir, lambda into L.
Exactly. So lambda L will not matter. L will cancel out. So you can get E equals to. And that is why I told you that what is the flux through the curved surface? The flux through the curved surface is E into 2 pi r.
Yes, sir. Sir, are you speaking something?
Oh, am I audible?
So for 2 seconds in the middle, I was not able to hear.
Am I
So your voice is cracking.
just a minute.
So now it's all right, sir.
Am I audible to you now?
Yes, sir.
Okay. So you can see clearly the flux through the curved surface is only this much, na?
Yes, sir.
And this flux is spread in how much angle? 2 pi.
Yes, sir.
So what is the flux through flux per unit angle? This upon 2 pi.
Yes, sir.
So if you remember the question that you solved in the last lecture, if you have a sheet placed somewhere here, it will only receive the flux through this angle. No?
Yes, sir.
I got your point. What I was trying to explain that day.
Yes, sir.
So that's why I said the answer will be like lambda L by epsilon naught into pi by 3 upon 2 pi, the fraction. So this flux is through this much angle. So we had only pi by 3 angle. And so the flux will be how much? Lambda L by epsilon naught into pi by 3 upon 2 pi, which is exactly lambda L by 6 epsilon naught. And we were supposed to compare with the formula this, and we got n equals to 6. If you remember the that question, do you remember that?
Yes,
Now,
sir.
okay. So now, do you realize that what was the first method?
Yes, sir. The number of field lines that go through the
Sheet. Correct. Okay. So that was exactly the question. And with that method, you can solve in one line. All right.
yes, sir.
So now, once we get the lambda, we can do the question for any type of cylindrical object which is infinitely large, or if the point is close to the finite center, both are the same situation. So now we have a question like this. So now we have a infinitely large cylinder. I can take it hollow and solid and whatever. Sorry. So yeah, this is infinitely long cylinder. And directly draw it like this. So this is infinitely large, but the cylinder itself is having its own radius, which we call capital R actually. And because it's a solid cylinder, we can take the volume charge density as rho again. So we are supposed to find the electric field for R less than capital R and for R. So there are two questions. You can apply the Gauss law and tell me the answer. Okay.
Yes.
So do it. And also after doing this, you have to plot the graph between the electric field versus R, because that is what I missed in the previous question. But nevertheless. So because we have two domain, one before R, other after R, so we will have two formula. Just do it.
Some
Yeah,
Sir, the graph, I'm getting like a linear graph which increases with r till the
yeah,
radius
simple.
and then decreases.
Exactly. That is the right answer.
Okay.
So can you
Sir,
do the, yeah, tell me. Am I
sir,
audible?
yes, sir. So the value of electric fields.
Yeah. What are the values? Tell.
So for less than the radius, I'm getting
Mhm.
rho r by 2 epsilon naught,
Correct.
and greater than the radius, I'm getting rho r square by 2 epsilon naught into 1 by r.
Correct. Very good. So yeah, excellent. So all right. So you got the answer. This is rho r by, I think, 2 epsilon. This is what you got, right?
Yes, sir.
And for outside, what you getting?
So rho r square by 2 epsilon naught into 1 by r.
Are you getting this answer?
Yes, sir.
So this answer is similar to lambda by 2 pi epsilon naught r.
Yes, sir.
But the question is, what is lambda? So lambda is defined as rho into cross section area,
Yes, sir.
and you can prove it easily, right? So
Yes, sir.
if you choose a particular length dl, just like this, so the charge will be lambda dl in terms of lambda, but in terms of density, you can add as rho into cross section area.
N into pi r square.
So lambda is basically a rho into cross section area or pi r square, whatever. Understood?
Yes, sir.
So the reality is lambda rho only, but we can express everything in terms of rho. Eventually, the rho is the real values. For any point outside, it is as good as a line charge. That is what we need to remember. Understood? And then you
Yes.
can just convert the lambda into the required formula. You will get the right answer. Is this clear?
Yes, sir.
All right. So now we can go to the next concept. So can I do it for the hollow cylinder? So let me do this first. This is the infinitely large. Or let me do it on the next page. So imagine we have a hollow cylinder. So now what we have is the infinitely large hollow cylinder, and sigma is the surface charge density, and the the radius of this cylinder is capital R. Okay, so this is the radius. So the question is again same. Find the electric field before and after. And now, is the cavity concentric? The hollow cylinder we can think as a big cylinder minus cavity, like you remove the cavity thoroughly, isn't it?
Yes.
So this is equivalent of a concentric cavity.
Yes, sir.
So you may take the thickness of the sheet as T. Maybe you need some thickness concept later on. And T is really small than half. That's why we call hollow. Okay.
Okay, sir.
So because the cavity is concentric, then the ambiguity should not arise. So we can say, yeah, this is 0. Can we say this is like 0 fluid inside?
Yes, sir.
But I'll prove it in a different way. But right now it is 0. So just you need to find the outer one, because that you can do is
Yes, sir.
the inner one is okay, na? The inner one is simple answer.
Yes, sir.
So just do it for the outer one.
Okay, sir. Sir,
Yeah.
sir, sigma r by epsilon naught into 1 by r.
Yeah. Sigma R by epsilon not R, right? Like this.
Yes, sir.
Yeah. Excellent. So again, this is the same formula, lambda by 2 pi epsilon r.
Yes, sir.
But now what is lambda here? So lambda in terms of sigma will be sigma into perimeter.
Yes, sir.
So sigma into perimeter is for lambda. So you can see this is the moment you substitute here. You get the exact answer, right?
Yes, sir.
So for anything cylindrical, the only formula that one should remember is the line charge. The rest we can convert. For outer point, we can do it for inner point also, but we have to just change the. So let me do it for the solid with this method. Let's say I'm trying to find here answer. Okay, at a distance r. So what I'll write is, I will write lambda upon 2 pi epsilon naught r. But what is lambda? So it is rho into pi small r square. That's the problem.
Yes, sir.
So you can see the answer is same, right?
Yes, sir.
For outside, we have to restrict the answer up to capital R only. That's why we have the difference in the answer.
Yes, sir.
Do you realize this what I'm saying? The outside, the inside.
Sir, you're talking about the continuity of the charges, right, sir?
Yeah. So for the inner point, the lambda should be substituted as per the the radius of the cross-sectional area of the cylinder taken. For
Yes, sir.
outer point, because the charge is not everywhere, the charge will stop only at capital R. So we take the answer up to capital R.
Yes, sir.
So what I am trying to say that there is a single formula which can derive all answers. So what one should just remember is this much, and that is more than sufficient for all cylindrical problems,
Yes.
isn't it?
Yes, sir. We substitute lambda as per its
Yeah.
value.
Yeah, correct. So now imagine we can create something like this. So now cavity problem will come here as well, but in this case, the cavity will be like a parallel to the axis. So we are not going to take the concentric cavity because concentric will give zero field inside.
Yes, sir.
But what if the cavity is parallel to the axis? So the way to represent is, we don't draw the lengthwise. Rather, what we do is,
Top view.
yeah, top view, exactly. So we draw like this, which looks like a sphere problem. No much. So this is the top view of infinite center.
So are you speaking something?
No, no, no. So now you can do the same thing the way we did earlier. So this is the center, and this is the center of the big one. And you will see that, okay, there is a pattern in all such questions. So what is the electric field at a point P? That is the first question to you. And then also draw the electric field lines within the cavity. And that's it. So can you tell me the answer?
Okay, sir.
Yeah.
So can you just come back in a minute?
Yeah, sure, sure.
So what are we to find exactly?
Electric field in the cavity, inside the cavity.
Okay. So that is just rho by 2 epsilon naught into O dash, right? Sir?
Exactly. Excellent. You got the idea, right? Now this is simple. Now these things are not very difficult. So it is rho O dash divided by just the, instead of 3, the 2 will come into picture, right? Nothing else.
Yes. Sir.
And then we can also create a variety of problem from here also. We can do the same trick. And okay, let me do the field lines. So here the field lines will be parallel to this one, right? All
Yes.
electric field will be like this. And the field will be 0 only when the cavity is concentric with the big cylinder, right?
Yes. Sir.
Because if it is concentric, then O dash becomes 0, isn't it?
Yes. Sir.
Okay, so this is a big takeaway from the entire discussion. And we can do the same. We can also create the superposition formula and so on. So because these things are similar, so we'll not indulge in those calculations. So we can leave it here. Okay. So after cylinder, what comes next? Yeah, in fact, you can also have the problem here. See, I mean, we can go back here. So okay, let me do this once for you. Okay, maybe you should practice at least once. So what if we have a solid cylinder which is infinitely large, and oh, sorry, and the radius of the cylinder is capital R, but the charge density is variable. So now can you do it the same thing? Find the electrical before and after.
Yes. Sir.
Yeah. So here taking the, okay, what is the important learning is how to take the elementary part and then do the calculation. So try this out, then I'll check.
Okay. Sir.
So you know how to take the cylindrical shell as elementary?
Sir, I'm getting the answer.
Yeah.
Sir, I'm getting the answer for r less than r as rho naught r by epsilon naught into 1 by 2 minus r by 3r.
Rho naught upon 2 epsilon naught into r minus r by 3.
Sir,
Like
small
this?
r by 2 minus small r by 3 capital R. Sir.
Okay. Small r by 3 capital R, like this.
Sir, and then rho naught by e epsilon naught, sir. 2 is not there.
But that should be r squared because that will be dimensionally incorrect otherwise.
Yes. Yes, sir. So when I originally told the answer, I took the smaller outside.
Okay. Okay, so you got the 1 by 2 kind of thing, right? Like this?
Yes, sir.
That's fine. That's correct answer. It's a quadratic, and the maximum will get at 3r/4 if you solve.
Okay, sir.
Yeah, that's good. So I hope you have taken the elementary like this, right? A cylinder of some length.
Yes, sir. 2 pi r dr into L.
Excellent. Very good. You know this method, right? Yeah. So that is what I just wanted to see. Rest is simple. All right. So after doing this cylinder, now we can actually move to the sheet part. So we are done with the sphere and all. So infinite large. So let's say we have a now if we have a infinite sheet. So no matter how big is the sheet, if you when we talk about the infinite sheet which is non-conducting, so it will have some thickness. So the thickness part we cannot avoid. It is not like it is having zero thickness, isn't it?
Yes, sir.
It will have some thickness that we must understand. And the charge which I am talking about is actually charge in this thickness. It is not on surface one. So when I say non-conducting sheet, the charge is part of the volume, not the surface only. So it is not about few layers of surface. It is about the entire thickness of the surface. Now sigma is a concept that depends on because the thickness is really small. We prefer to represent this by sigma. And the thickness actually plays a role. So if you want to understand the thickness part, let me do it separately. So this is the maybe side view of infinite sheet. And this is the thickness part. So the rho, which is the reality, and the sigma, which is the convenience, you can say, we want to represent in terms of sigma. We can relate these two, right? So how we can relate? sigma will be how much? So we take area, like you take some area.
Sir, rho into dA into T will be equal to sigma dA.
Yeah, so it is like if you think about some small patch of cross-sectional area, let's call it S or whatever. So the sigma, the charge you can correlate is sigma into S is same as rho ST, correct?
Yes.
So the sigma is nothing but the density, the volume charge density into thickness. So when I say sigma, it means I'm just trying to represent the area-wise answer instead of writing the volume. So the first thing that we must take care of is that sigma, the way we define for the non-conducting sheet is thickness of the sheet into volume charge density. And charge is part of the volume, not the surface, but the thickness is so small that we essentially call it surface. Okay, this
Okay.
part is clear.
Yes.
Now, because it is a infinite sheet, so no matter which point you choose, that's my let me take.
So the charge is within the thickness
Yeah,
because of its non-conducting nature.
yeah, correct, correct. So imagine if I draw again, let me do this. So because it's a infinite sheet, so I can draw any XYZ coordinate, and I can say that the XY axis will divide into 4 equal quadrants, right?
Yes.
Black is better. The red doesn't look like a charge. So now every point which you can take above the sheet will have electric field to all the 4 quadrants, right? And because it's infinite, so no matter which point you choose, every point is on the z-axis, isn't it?
Yes.
So if I take a patch here and think about, okay, let's say this patch is creating a field, then I can take a exactly symmetrical patch on the other side. And I can also get the one patch here symmetrically and one patch here. So if you look carefully, that every point will have net field only along the upward direction, right?
Yes.
So because of symmetricity, it doesn't look like it will happen, but all will actually point towards the z-axis. So the net field, just a moment.
Because
So now what you can realize that no matter which point you choose, the net field is going to be vertically upward. Okay. So for the
Yes.
entire sheet, the net field is always vertically upward, no matter where you choose. Let me remove this. So the electric field at any point above the sheet will be upward. And that is everywhere. And if you choose any point below, it will be having the field downward one.
Yes.
So below means downward because the field will be like this. Now what I am not representing is the field within thickness. So that we are ignoring because that's why we are learning about the sheet. But we'll see the field within the thickness as well very soon. So we'll see what happens inside as well. Now because the electric field is in both directions and normal to the sheet, so what kind of Gaussian surface will be helpful to us? Any surface which is having a surface perpendicular to this part, right?
Yes, sir.
If you create any surface, no matter cylindrical or cuboid or hexagonal, if I have a surface which is having a flat surface above and a flat surface below, that is sufficient. The flat surface may be circular, maybe not be circular. That's not important. So imagine if I give you the idea, if I create a hexagonal box shape like this, and then we have parallel sides like this, and then it goes below the surface, right? And then we have the same thing. Even this is the suitable one. This kind of Gaussian surface will also work because the side which are normal to the surface will not contribute to flux, right? Because the field will just go like this, parallel, isn't it?
Yes, sir.
So the flux will be only through the flat surface, right? The surface which is perpendicular. So it's good to assume a Gaussian surface, something like this. So let me draw the Gaussian surface. Then this is the part of the surface, and then it goes below. Just to make it a three-dimensional feeling, let me make it more. So you can see that. So we have three layers. So this layer is representing the charge part. So if I say this area is S, this is also S, this is also S, correct?
Yes, sir.
So the flux through the cylinder is how much? What is the flux part? So if I say the electric field is E, and what I said is electric field is going to be uniform. Okay. So whenever things are infinite, the field will be uniform. It will not vary. And therefore,
ES into 2.
yeah, so ES 2 times, right?
Yes, sir.
And this is charge inclusive with sigma into the visible area. Okay.
Yes, sir.
The surface area is S, so this is the charge upon, and therefore the E turns out to how much? Sigma upon 2 epsilon naught. But what is sigma here?
So surface charge density, rho T.
Rho. Is this clear? So for non-conducting sheet, the formula is sigma upon 2 epsilon naught, where sigma is this. So the answer is, you can also write as rho T upon 2 epsilon naught. Okay.
Yes, sir.
Okay. So now what is most important is called the connecting sheet. if you have the infinite connecting sheet, then okay, I will not draw the sheet that way. So I'll just, this is the sheet. This is the thin sheet. But if I zoom, it will be better for you. I will just make it thicker like this. Intentionally, I'm doing it intentionally.
Okay.
And now the charge which you know, if you give charge to this sheet, the charge will only appear on the top layer on the right and top layer on the left, because the electric field within the conductor is zero. So conductor will never accommodate extra charge in the volume. So any excess charge given to conductor will only be part of the surface. So this is the two atomic layer which I am just exaggerating here. So in a way, the way one should understand the connecting sheet is the charge is provided on the two extreme surfaces on the left and the right. And the charge will be part of not the entire volume, but few layers of atomic layers, it's called surface, which is equivalent of two non-connecting sheet. So I can think, okay, if this is the volume in which charge is residing, so if I call this thickness as the critical thickness, thickness which matters, then the rho of this surface and the rho of this surface will be same. I mean, surface means volume. So conductor actually allows you to create two non-connecting sheet. And therefore, the sigma in this case will be rho into T critical. But this is not the rho into thickness of the sheet. So this thickness is not considered at all. Understood?
Yes.
Which is not equals to rho into T. And the TC is having dimension up to few atomic layer. Let's call it 10 angstrom. So the one atom is roughly 1 angstrom in dimension. So 10 atom will be 10 angstrom, which is almost negligible, right? This 10 angstrom is nothing. We know it's a 1 nanometer, which is very, 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 very small. Understood?
Yes.
So the idea is when you give some charge to a conducting sheet, the charge will actually divide half on one surface and half on the other, assuming T is very small. Okay.
Yes, sir.
And that is why if I ask you what is the rho in this case, so rho for the conductor is, let's call it the rho C, the conductor density for conductor. So rho C is defined as Q by 2 upon area. Understood?
Yes, sir.
Or you can say area, let's like this. And therefore, if I compare the answer with the previous case, here if I give charge Q, the Q will be part of the entire volume. So the density in case of non-conductor, let's call it NC, is actually Q upon area. I'm sorry, what am I writing?
So how is it Q upon area?
Sigma, just. Sigma, actually, what I made the mistake is sigma. Sigma in this case is?
Q upon.
So, okay, the rho you can define as Q upon AT actually.
Yes, sir.
Area into T. This non-conductor will have, I think I missed this part here.
Yes, sir.
This is AT, volume. But this is ATC. Understood?
Yes, sir.
So the sigma in this case and the critical sigma is rho C TC. So that term, this turns out to be Q by 2A. So sigma for conductor is Q by 2A, but sigma for non-conductor is how much?
Q by A.
It is Q by A. So symbolically, it may look like one is bigger, other is smaller, but the reality is both gives the same field. It really doesn't matter whether we have the connecting sheet or non-connecting sheet. If you supply same charge, they will create the same. But if you supply different charge, then the answer will change. So when you say they have same sigma, so actually they have different charge. Understood? So if we have one connecting sheet and another non-connecting sheet, and if I'm saying that they have same sigma, it means they have different charge, because same sigma, the way we define sigma is different, no? Isn't it?
Yes, sir.
So the derivation, okay, I haven't given the derivation here. No? So okay, we have done this, but you can draw the Gaussian surface like this. So we draw the Gaussian surface just like this. From the side view, it looks like this, and the electric field will be like this. On the right, like this. On the left, will be like this. Correct?
Yes, sir.
And the flux will be again the same 2ES and the sigma by epsilon naught. So we got the answer E equals to. So non-connecting sheet gives the answer sigma by 2. Okay. Coming back to this. Okay, we have done this, but coming back to here. Now here, the moment we have a conductor, the better way to draw the Gaussian surface is this. So you can draw either this way. So take the one part within the volume and other part outside, or you can take both parts outside, just like this. So the second one is similar to the non-connecting sheet, but the first one is really easy, and you will also find this convenient because we know the field here is 0.
Yes, sir.
Now this is also okay. The second direct way of taking the Gaussian surface is also okay, because we know luckily that the field on both sides are equal, right? So the
Yes,
field on the left and the field on the right are equal. So we can choose any one, but one should not be choosing this way if the fields are different. Are you getting the point? What I'm saying?
so
So
we
if
should
this
not be
field,
choosing the second case if the fields are different.
yeah, because that will give you the two variables. No? If I may say E1, E2, then you cannot solve the question, isn't it?
Yes, sir.
So if I say both fields are equal, E and E, then the answer is same. But if I say E1, E2, the flux will have two variables, no? E1, E2. So we need two equations to solve, right?
Yes, sir.
But if you choose the first scenario, then you can get electric field in each side separate without any difficulty, right?
Yes, sir.
So the Gaussian surface like this is helpful in case of conductor, but we can choose both. So what you can write is E into the cross section equals to sigma into cross section upon. So the answer is simple. In for connecting sheet, the answer is sigma by epsilon naught. So it looks like formula wise that the electric field of connecting sheet is twice the electric field of non-connecting sheet. So formula wise, yes. If you assume sigma is same, then of course the connecting will have a stronger field than non-connecting. But if I supply same charge, then field will be same, isn't it?
Yes, sir.
How? You can see here the answer is, what is sigma here? Q by 2A.
Yes, sir.
Now look at this in terms of charge. If you try to answer in terms of charge, what is sigma here?
Q by A by, oh, yes, sir.
So in terms of charge, if they have same charge, then field will be same. If they have same sigma, then answer will be different, isn't it?
Yes, sir.
So this is the question from the multiple choice question SC Verma, that if a connecting sheet and non-connecting sheet given same charge, then which one will create the bigger field? Or the field will have will be equal, unequal, and so on. So that is how the question is there. Okay.
Okay, sir.
So So E connecting sheet is Q by 2A epsilon naught. So now these are the formula. And with this, we complete the derivation part of Gauss. Like in various situations, you can find the electric field. Okay,
Yes, sir.
it's clear.
Yes, sir.
All right. So what next? So next we can go to the potential part, right? So we are done
Yes.
with the field part. Just let me see if I miss some. Just a minute.
Sir, I speaking something? Some? Okay. Oh, okay, sir. Bye, sir. Thank you, sir.
Am I audible to you? Hello, hello. No, so it's problem.